is the second part of the EC tutorial on information design. In the first part, Konstantin has talked about some algorithmic fundamentals of information design. In this part, I will talk about some recent kind of a new problem along the space. I want to kind of start by mentioning that it's really exciting to see many familiar faces here. Actually, many of the results I'm going to talk about today are from the audience. So I think I'm basically presenting on behalf of many people. And I also want to start by briefly remarking that originally I thought I just mentioned new frontiers, which turns out to sound too large because I did some search on Google Scholar about information design in 2023. There were really more than 100 papers on this. So I decided to add some new frontiers. So as you could imagine, this tutorial is going to slightly bias towards kind of algorithmic studies due to the nature of the work that I'm familiar with. But I'll try to kind of make it as accessible as to general audience as possible. Okay. So yeah, let's get started. So I guess the goal for this talk is try to kind of connect the information design to a few different problems, and I decided to pick the following 4 topics. The first is about the information design with monetary transfer, and that's kind of the problem of the optimal pricing of information. Second part is about the information design optimal stopping problem, which I think is a very there's a rich literature at least in computer science about online algorithm in those, and we're going to see how information design actually is kind of a very natural in those setups as well. The third part is about the information design equation problems, particularly, recently there's a big surge on contract design, which is relevant to this. Let's see. Can we get to this one? I see. Let's see. This one, right? Let's see. I'll put it on the bottom. Okay. Good. So the third part is very relevant to the information design principle agent problem, particularly like the contract design problem that we have seen a lot recently, at least in the EC community. And finally, is about relaxing one kind of a crucial constraint in information design, which is a commitment constraint. And there we will list to some problem called chip talk, and I'll kind of briefly mention there and some exciting open problems there that we're currently thinking about. I want to mention that, so for this part of the tutorial, I will primarily focus on the problem definition and the results that we have in those space, but less focus on the techniques, because I think, for those techniques, you can definitely check it on the reference papers. And moreover, all the relevant papers on every slide will be listed at the bottom of each slide. And we will also post the slides on the website after the tutorial. Therefore, you can really see, what are the papers that I'm talking about. Okay, so if you didn't see what is the paper, don't worry about it. You should be able to find it in the online slides later. Good. Okay, so let me get started into the first part. It's about information design with monetary transfer, which is really the problem for optimal pricing of information. There were many motivations about studying information pricing. I think it's also have a kind of a rich literature in the econ, at least it dates back to 30 years ago. But I think it starts to become more popular recently, and also I personally become very interested in this as well. And one of the major motivations I'm interested in it is because it's very closely related to how to sell machine learning predictions, which, as you could imagine, is on the way of becoming a very big problem. And in fact, there are already very large commercial platforms that sells machine learning models and machine learning training service, as well as machine learning predictions. 2 prominent examples are Google Cloud Vertex AI, which is machine learning service platform that you can buy those ML service. Another competing large platform is Amazon SageMaker. These are just the 2 examples, and there are many smaller platforms as well. And at a high level, you could imagine the problem there as part of the problem there as there were some users who are interested in predicting something, and they can turn to this platform and try to purchase those predictions. For example, maybe you are a restaurant owner. If you tell Google what type of food you can produce and what are your location, maybe if you're in Chicago, maybe you are around the University of Chicago or you're in the downtown area, then you can ask Google, can you predict what is going to be the demand for my restaurant if this is some kind of a basics for the restaurant, and Google can provide this prediction as a service and therefore charge this local restaurant for some amount of money. And this is already happening for maybe not at the restaurant level, but many kind of slightly larger startups are purchasing predictions from Google. And I would imagine it will only become kind of a more popular given this kind of explosion on the large language models or large machine learning models in general, or sometimes people nowadays call it foundation models, which can make prediction for different tasks of similar spirits. At a high level, how is this problem related to persuasion or information design? Well, you could really think of this as a problem where a sender try to persuade a receiver to pay him as opposed to persuade the receiver to take certain actions. You don't care about whatever action receiver takes. You only care about how much it pays you. So that's kind of the pricing of information problem. And we'll make this kind of intuition slightly more concrete in the coming slides. By the way, feel free to let me know if you have any questions along the way. I think it's hard for me to really see any interactions because there's nothing on my screen, so feel free to stop me if you have any questions. Okay, so and to motivate this kind of problem and also give you a kind of a concrete example about what such a model can be like, let me describe a very basic model about monopoly pricing of information. So for those of you who know monopoly pricing of the classic good, this is pretty much very similar, except that you are pricing information. So here we have one seller and one buyer. And, if you are in the previous section by Constantine on information design, seller, you can think of him as the sender, and you can think of the buyer as a receiver. And one example is the seller maybe Google Cloud, which can make a lot of predictions, and the buyer maybe is some kind of a small restaurant owner who is deciding, whether he wants to open a restaurant here or don't want to open a restaurant here. So this buyer is a decision maker who faces a binary choice. Either it's an active action or it's a passive action. So an active action could be, I want to open a restaurant here, or maybe I want to approve a loan for some if you are a loan company, or you want to investigate some StockX. That's a passive. That's an active move, and the payoff for the passive action, which is 0, meaning you don't do anything. And if you don't open the restaurant, you don't get anything. So your utility is 0 there. But the payoff for the active action is a value function V that depends on Q, which is some kind of a state of nature. It's just like the state of nature in information design. And this buyer also have a private type, which is some private information the buyer holds. In this restaurant example, you could think of VT in the following simple format. The Q maybe is the demand. If you open a restaurant here, what is the demand you will get? And the T maybe is the profit per kind of a consumer, and that's a private information to the owner. It's something not known to the seller. And there may be some operation cost, so that leads to this linear utility function. But this is just one way for you to think about it. In general, we should be able to handle convex value functions in general. So that's the payoff for the active action. As I said, the buyer's private type T is drawn from some public known distribution, just like the standard monopoly pricing problem. But the interesting part here, or the new part here, is that the state of nature Q is something that the seller can learn, and so the seller knows and can reveal partial information about the Q. In this restaurant example, Q is basically the demand of your restaurant, and that's something Google can try to predict and then reveal this kind of a learning information about Q to the restaurant, and then profit from this information application. Okay, so then this naturally gives rise to a natural mechanism design question that is just like in persuasion, the seller here like information design, I guess. The seller here designs a signaling scheme about the state of nature Q, but his goal is to not persuade the buyer to take certain action, but instead try to maximize charges from the buyer. So that's basically a variant of the information design problem here. And okay, so how can we solve this problem? In this kind of a recent EC paper, people were able to show that in this, even though you can design the signaling scheme in general can be very complicated, it turns out that selling threshold experiments where it suffice for you to achieve optimal revenue. Recall that the buyer's value is basically a V function for the active move. So a threshold experiment, particularly a personalized threshold experiment, which is equivalently people call it a signaling scheme, is determined by some threshold function theta, which depends on the buyer's type T. And this threshold experiment or signaling scheme simply reveals your predicted Q is greater or equal to this theta T or smaller or equal to the theta T. And importantly, this threshold is personalized for different buyer type T. Okay. And it turns out that given this understanding, and we are able to fully characterize what the optimal mechanism for the problem I described to you, what the optimal mechanism is going to be like. It turns out that it also relates to the virtual value function as developed by Milson. I guess for this community, we're familiar with this virtual value function by Milson, but it turns out that here we need a little bit more things. In particular, I'm going to call the virtual value function the classical one, developed by Milson. I'm going to call it a lower virtual value function. The reason I call it lower is because there's a opposite notion called upper virtual value function, which is simply t plus a positive number. It's called a lower for Milson's original version because it's a t minus some positive value. And what is more important is I need something called the mixed virtual value, which is simply a convex combination of the lower and the upper virtual value function with the convex coefficient C here. It turns out that this mixed virtual value function naturally gives rise to the optimal mechanism. I'm not going to show you the exact statement of the result, but intuitively it's something like this. It turns out that the following mechanism is actually optimal for the previous problem. So essentially, the mechanism is going to use threshold predictions theta star t, which recall that it's a threshold experiment, and the theta star is simply the mixed virtual value function of the type t. Recall that the theta star depends on t, and that's just like the mixed virtual value function. And moreover, use a kind of a payment function, which can be calculated in closed form. I'm not expecting you to look at the payment in detail, but just to realize that there's a closed form way to calculate this payment function. And the only thing I didn't tell you here is the mixed virtual value function have a convex coefficient c, and that c can also be explicitly determined by the problem setup. And this basically intuitively can tell you that there's a kind of a closed form characterization about the optimal mechanism for the previous problem I described. Okay, so that hopefully gives you some kind of a flavor about what kind of information design problem you can think about in this, in this space, and what kind of result you might be able to expect. And also we can learn some interesting economic insights from this result. First of all, as you can see, the optimal mechanism actually not sell the state of nature Q directly. So it never reveal Q directly to you, but it's only selling you the processed information. It's like a threshold testing to tell you your Q passed some threshold or not. And moreover, this threshold is actually personalized. So for different user type, this threshold is also different in order to somehow kind of account for the different risk level that the buyer can take. And this is very much like the private persuasion problem as mentioned by Konstantin in the classic, standard information design setup. And because of this kind of a power of personalizing your signaling scheme, that actually gives you significantly much more power to price discriminate the buyers and therefore extract more revenue. And that's actually a very interesting phenomena where you can really explore and design a mechanism whose revenue is much higher than the situation that you are not allowed to use price discrimination. Okay. And in this kind of a simple setup, it's nice in the sense that we can derive the optimal mechanism in closed form. But unfortunately, it turns out that in general, if you look at more general models, closed form optimal mechanism becomes much more difficult to obtain. So here's a kind of a natural generalization of my previous setup. So in previous setup, I only have 2 actions, but in general, you could imagine the buyer, who is a decision maker, may have n actions or even have infinitely many actions. And in my previous model, the buyer have a very simple utility function. His utility for one of the action is 0, for another action have a non-zero utility. But in general, you could imagine the buyer has an arbitrary utility function that depends on his action I, depends on the state of nature theta, and also depends on the buyer's private type T. And the state of nature and the buyer type are assumed to draw, similarly assumed to draw from distributions. Pretty natural generalization of the previous setup. And it turns out that the people have studied this problem actually 10 years ago. This is a very interesting paper by Babayev, Klemberg, and Renato. So in their paper, they developed the revelation principle for this general problem, and also show that there's a polynomial time algorithm to compute the optimal revenue maximizing scheme actually. But it turns out that there's some kind of a drawback with this previous result. So the first is that their computation is actually extremely complex, even though it is polynomial time. In fact, you need to go through every vertex of the buyer's posterior polytope, which you need to prove that the vertex is actually polynomial many. So you can enumerate them one by one, and for each of the vertex, you need to solve some larger linear program. So that's their algorithm. And another kind of a drawback is the optimal mechanism turns out to be unrealistic in some situations. For example, their own paper have an example to show that there's a kind of a simple example where the buyer's value is simply between 0 and 5. But their optimal mechanism has to ask the buyer to deposit roughly $25,000 first. And then with some probability you will return 0 to the buyer, and with some probability you will return 50K to the buyer. And they show that this is the optimal mechanism, which yields optimal revenue at most 2. So you can see there's something unnatural happening in this optimal mechanism. That's really a question as to study, to kind of lead us to study, can I develop a mechanism that's kind of a simpler to consider and also become kind of a more natural to implement in reality. And that leads to a recent work by Yiling, me, and Shuran before, which kind of tried to simplify their algorithm. And it turns out that actually this is doable. We can simplify the algorithm really just to a single convex program. So you only need to solve a convex program to get the optimal mechanism. And moreover, we allow you to set the upper bound for the payment. So therefore, you can kind of constrain your payment to be at most some number. So therefore, it will never happen that in order to get revenue 2, you need to charge them 25K. So the key idea of this paper is basically we are able to show a simplified or succinct version of the revelation principle, and by proving that there exists an optimal mechanism that is in a very succinct format. And this format is basically, this kind of a simple mechanism proceeds really like a consulting procedure, just like in the consulting industry. And that's why we simply call this mechanism the consulting mechanism. So what is the mechanism like? Well, so basically the procedure as follows. First, we elicit the buyer's type. You tell me your private type T, and then I'll charge you XT amount, which is the payment you need to pay me. And then I'm going to implement a signaling scheme, pi T, for the buyer, which simply recommend an action I to the buyer to take. And I'm going to recommend action probabilistically based on some kind of a probability, which, if you basically based, as in the part 1 we have already seen, it's just the signaling scheme that, it's just a direct signaling scheme in Constantine's language. Okay, as you can see, such a kind of a consulting mechanism can be described by a menu, because for every buyer type T, you have a payment XT and you have a signaling scheme pi T. right? It's really just the manual of the mechanism. And as you could easily imagine, like any standard kind of a mechanism design setup, you can show that this manual can, without loss generality, be incentive compatible. That means the buyer should report the true type, and the recommended action should be obedient. In other words, just like in consulting surveys, where people recommend you action, when the consulting company recommends you some action to take, it's typically your best action to take, and it's also happening here. The recommended action should be obedient as well. It turns out that the optimal consulting mechanism, this format with the manual PyTXT, computed by a convex program that I'm going to show you next, is an optimal mechanism for the previous general problem. Okay, and there's a convex program to compute the optimal consulting mechanism. I'm listing this kind of a convex program here, but I'm not expecting you to really look at the detail. Just try to illustrate that this mechanism is pretty much like the standard thing that you saw before. For example, the objective is simply just the expected revenue, the expectation over the charge. And the first constraint is basically the truthfulness or incentive compatibility constraint. So if your true type is T, you should report T as opposed to T prime. The second constraint is the so-called participation constraint. So participating in the mechanism should be better than you just behave on your own. And finally, it's the obedient constraint, basically saying if you are recommended some action, you should just take that action. That's what the direct information design signaling scheme is requiring, basically. So, and that's pretty much the convex program that computes the optimal mechanism in the previous problem. Good. Any questions here? Okay. And this is just one line of model, and in the literature there are definitely many other models about information pricing. Here I'm just highlighting some of them, particularly those I think inspired really our work. So perhaps one of the most well-known one is by Bergman, Bonatti, and Alex Molly. So they consider an analog monopoly pricing problem as we did, except that their private type for the buyer in their setup is the buyer's belief about the state of nature, not the buyer's utility uncertainty, as in our setup. So that's the core difference. But they're able to analyze the structure of the optimal mechanism, and are able to characterize the optimal mechanism under some special utility structures. And then there's a follow-up paper, I think, in computational study, which develops algorithm for this problem. And also more recently, in last year's EC, there's a paper that characterizes how much revenue we have to suffer if the seller is not allowed to do price discrimination. The seller have to use the same signaling scheme and the same payment to everyone. How much revenue loss you might need to suffer? And it turns out that there's a lot of revenue loss you have to suffer. And another paper by Inkai studies what happens if the buyer can obtain additional signal about the information, before coming to your mechanism. And another paper by Kai-Hao Yang is in a more kind of a structured setup, and he studies how to sell information about the market segments to a producer, so that the producer can further, price discriminate the consumer. So how to sell such kind of a market segment information to the producer. And I think there's a working paper from MIT studies how to sell information to multiple and competitive players. Previously, most model I mentioned before is about monopoly, pricing information to a single buyer, but you can also sell information to competitive buyers. And there's ongoing work on this. I think they also have a follow-up work on this actually from the same team of members. And I think more usefully, there's a very nice survey by Bergman and Bonatti on, it's an econ perspective survey about markets for information that you can check out. But I think there seems a lack of survey for algorithmic perspective or operational perspective of this information pricing problem, so far as I know. Good. Questions here? Okay. So that's the first part about pricing of information. In the second part, I'll switch the gear a little bit and talk about information design, optimal stopping problems. optimal stopping problem is kind of a general class of problem that has attracted a lot of attention in computer science, particularly in online algorithm design community. There were many examples in this domain. I guess different people have their own different favorite problem, but one of my personal favorites is the so-called Pandora's box problem. Is a kind of example of optimal stopping problem. I like it because it's really simple and easy to understand. So what is a Pandora box problem? It's basically a kind of an online decision making problem. There were n boxes. Box I has a random reward Ri, draw from some distribution Gi. For simplicity, let's assume they all support on 0, 1, which does not matter too much. So an agent who is you try to kind of open the box one by one and try to collect some reward. But open the box I have a cost Ci, but the benefit for you is that you can observe the realized reward Ri from that box. And the problem for the agent is, you can claim the reward from one of the open boxes. So even you open many boxes, you can only claim reward from one of them. But you suffer cost for opening any boxes. So there's really a lot of applications for this problem. So for example, let's say you are venture capital, you're looking for a startup to invest. Then you need to talk with the different startups, and you have opportunity cost, which is the CI, to open those boxes. But at the end of the day, you can only invest one of the startups, because you only have a limited budget to invest in them. So that's exactly Pandora box problem. If that's too far from, at least too far from me, but some problem that's very relevant to me is PhD open houses, for example, right? So there maybe you got multiple PhD offers, but you want to decide which university is the best to attend. So you're gonna visit the different universities. Of course, there's opportunity cost for each visit, but at the end of the day, you can only attend one of the universities. So that's exactly Pandora box problem as well. Finding newspapers or channels to subscript, that's another Pandora box problem as well. The question here is to study what is the kind of a utility maximizing search policy that can maximize your expected utility, that can help you pick the most rewarding box, but suffer the minimum cost. I'm not going to describe the detail here, and it turns out that there's a really elegant and a simple greedy policy that is optimal for this problem. And it's very simple. That's actually the reason I really like it. Simple and non-trivial in some sense. And I just want to mention, this is just one example of the optimal stopping. There are many other optimal stopping problems. I think one of the most famous one you heard about probably is the secretary problem. Is another variant of the optimal stopping problem. There, it's kind of a similar flavor of this Pandora box, but you have a different reward selection criteria, and also typically you have a different constraint on the order to open the box. For example, sometimes you have to follow a fixed order. You're not free to pick which one to visit next. Those are kind of how typically those problems differ, but the flavor of those problems are very similar. I wouldn't say very similar, but shares kind of a similar flavor. And it turns out that it's kind of a really interesting thing to observe is that, even though there have been a lot of study of those online optimal stopping problem, but typically people always think of this box as static. So there's truly a box there that, it doesn't change at all. But that really, it's an interesting thing because, in many real world applications, those boxes are not a static box. They're a clever agent that are thinking in their own and have their own objectives. And that really leads us to study Pandora box with strategic boxes. And, almost in the previous motivation I mentioned, that they are strategic boxes. For example, let's say you are a venture capital, search for some good startup to invest. As you could imagine, startup would never want to reveal the true rewards to you, to a venture capital. They would kind of advertise their product, try to kind of selectively, partially reveal their information to the venture capital. So every startup is going to do this. And that's, really the strategic box, not a static box. Similarly, for the PhD admission during open house, typically, I would imagine, during your PhD visit day, the university, the department or the university wouldn't reveal complete information to you. It's also kind of a selective revelation about, the status of their department. So that's also strategic box. And if you want to search for newsletter to subscribe to, and those are definitely strategic strategic newspapers. They want to attract you, they want to charge you. So they're also revealing information about their news content or news qualities in a very strategic way as well. So that's really motivates us to study these strategic boxes. And that leads us to study this kind of a competitive information design in Pandora box with the strategic boxes. Essentially, the only variant is just to make the box strategic. They have their own objective when they're deciding what information to reveal. So every box tries to maximize the probability of being chosen, and they may signal partial information to increase their chance to being chosen, if that helps. And the question we are trying to understand is what's the equilibrium among those boxes, assuming the agent, was going to follow some kind of optimal search strategy. For those of you working in game theory, particularly in stack overlay game, this is really a multi-leader, single follower stack overlay game. Every box is a leader, and the agent is the only follower who observes the leader's strategy and decides how to act. And our main result is basically we're able to characterize. So we have basically two main results. The first is we're able to somehow relate the agent's utility with the order of the informativeness of the distribution in the Pandora box. So we call this information order in Pandora box. Particularly if I use UGI genactive to denote the agent's optimal utility in the Pandora box, where GI is box I's distribution, and the genactive contains all the other boxes rewarded distribution, standard game theoretic notation. Then we have the following result. GI is more informative than H if and only if the agent's utility under GI is larger than utility under H. So this basically provides a kind of a characterization in terms of the Pandora box utility for informativeness of a distribution. So that's kind of an alternative to Blackwell's kind of information order. So Blackwell characterized information order in terms of decision-making problem. We basically are able to characterize this order in terms of Pandora box agent utility. The second main result is basically utilizing result one, we're able to fully characterize the symmetric equilibria of this competitive Pandora box problem in a symmetric environment, meaning every box have the same distribution, but IID, basically the box have IID distribution with the same cost. In this situation, we're able to fully characterize the equilibria. Actually, it's not only about the characterization. The equilibrium actually tells us some interesting conceptual messages. For example, it tells us kind of when you would expect transparency or more informative box information relation in Pandora box. In particular, more boxes or more competition. You have many boxes. That would lead to more transparency. That would kind of encourage boxes to reveal more information to the agent. Another observation is that the larger inspection cost would also lead to more transparency. So if inspecting the box takes the agent a lot of cost, then that actually would make the drive the equilibrium towards more transparent information revelation. And this result also strictly generalized to other recent works, which corresponded to a special case that 0. Okay, and this is just one particular setup with one particular kind of a research question. In general, there are really many decision making or search problem involves this kind of a costly information acquiring or acquisition, just like in Pandora box. And very often in these problems, information providers are strategic. I think if you look at the security problem, it's also similar. It's very, almost in many natural applications of the security problem or the profit inequality setups, their agents are strategic, the box are strategic. And there are many other kind of famous optimal stopping problems like option trading, house selling, parking. Those are very classic optimal stopping problem. I'm not aware of much kind of information design perspective to look at those problems. And there's really a lot of open problems. Immediately in our setup, we don't know how to do equilibrium in asymmetric environments. And more generally, information design in most of these optimal stopping problems, I think are largely open. Questions here? Okay, so I intended to primarily focus on the first two parts, but in the remaining two parts, I'll be kind of a more high level and just work you through that. What are some other new? These are very recent work. Actually, none of the papers are published. It's kind of ongoing work, but I think it's kind of interesting because it have a nice connection to many recent studies on contracts. So that's information design principal agent problem. The standard principal agent setup is basically the following. You have a principal and you have an agent. So the agents are, the action taker. So it have a bunch of action for the agents. Typically, you can also call them the effort level, as in many econ literature doing. So each action is going to make the agent suffer some cost, but also benefit the principal with some reward R. And but the core issue in this principal agent problem is the principal cannot directly observe the action. Instead, it can only observe some outcome of the action. So for example, if you take action A2, there's a 20% chance you will observe outcome A01, which is a very good outcome. With 50%, you will observe outcome O2 and the other outcomes as well. And that's really, you should really think of this as a signal as in the information design problem. And the principal want to reward the agent and somehow encourage the agent to take action that the principal wants, to invest a lot of effort for the principal, for example. So what the principal can do is to design a contract. So a contract, it basically tells the agent, if the outcome is some OI, I'm going to pay you some XI. So that's a contract. And you can solve this as a kind of an optimal optimization problem, compute the optimal contract. And now the interesting part to look at here is this mapping from action to outcome is really just the stochastic mapping, and it determines how much information the observed outcome carries about the agent's underlying action. And as you can see, this is really just the signaling scheme, which maps some unknown thing to the principal to a signal that the principal can observe. And in the literature, people also call this a monitoring technology in the contract design literature. But effectively or mathematically, it is just a signaling scheme. And that's how we realize the connection of this principal agent problem with the information design. So now let's look at a kind of a two simple example. One is what happens if this information relation was fully informative. That means the principal's outcome can observe the outcome, which exactly tells you what is the underlying action that the agent is taking. In this case, what the optimal contract would be? Well, if you spend 5 seconds to think about it, it will be very easy to realize that the optimal contract simply sets the xi equal just the cost of AI, because you know exactly what action the agent takes for each outcome, and therefore you just reward him for the cost of that action. Maybe you want to reward him slightly more, epsilon more about the action, but effectively just the cost. And in this case, you could imagine the agent is going to get a zero surplus because whatever his cost, he would only be compensated exactly by the cost that he suffered. He will not get anything additional. And that was viewed as kind of a less ideal situation in contract design, because we want the agent to share some of the welfare surplus from this interaction. So this is not a desirable outcome. And another extreme situation is, what if the scheme is fully not informative? So the principal cannot distinguish any action the agent takes, because any action is going to map to exactly the same outcome. What's going to happen in this case? And again, with 5 seconds thinking, you would realize that because the principal really cannot distinguish whatever action you take, so the agent would just take the least cost action, because the principal cannot tell what action he tells. And therefore, the principal can also predict that the agent is going to take the least cost action. So his contract is simply just the cost of this least cost action. And the agent, of course, is going to take the least cost action as well. And that is also regarded as a bad, potentially inefficient social outcome, which is not desirable as well. So the punchline I want to make here is that the lesson we learned is this information structure actually affects the total welfare a lot, and also affects what fraction of the welfare each player can share right? So that's kind of affected by the information structure. And most of the previous work has been on contract design, has been assuming this information structure is fixed exogenous. Is that anyone give me the structure so I compute the optimal contract? But the problem we're realizing is that in many applications, this information structure actually can be designed by some social planner or by some regulator, who want to kind of balance the share that each player can get from the welfare. And there were many examples. So one example is, the company maybe is the social planner who try to design some monitoring policy and it determines how an employee should report to his managers. And you want to design this way in a way that is not too transparent and neither too not transparent. We want to find the right level of transparency so that both of the players can get a good share from the created welfare. And this is moving this to a kind of a digital world. The freelancing platforms for matching work and tasks like Apple Work, they're gonna face this problem. They actually have to do this in a algorithmic way because it's kind of an online platform. And those are the motivations that really motivates us study to understand how information structure can affect the social outcome of this interaction, and moreover, how can I optimize information structure if the designer has some objective and also maybe have some constraint on the information structure it's allowed to use. In this recent ongoing paper, we look at the first problem and try to understand how information structure can affect the social outcome. I want to mention that this kind of the spirit of this paper is really similar to a seminal work, a very well-known seminal work by Bergman, Brooks, and Morris at AER, American Economic Review, which is called The Limits of Price Discrimination. They're trying to understand how the information structure design can affect the surplus between a monopoly seller and a buyer. So we're trying to understand how information structure affects the principal and the agent. So in the monopoly pricing problem, the information actually comes as related to the adverse selection because it's about the buyer's private type. In our case, it's related to a notion called moral hazard because the information is about the hidden action that's not observable by the principal. So this is usually called a moral hazard. It's a kind of an interesting connection and also difference from the previous work. In our paper, we're able to fully characterize what agent action and what principal agent utility pair can be induced from by designing the information structure. And we can account for both risk neutral and risk averse agents. We can also account for different kind of constraints on the information structure. I just want to mention that a similar question actually has been studied in previous econ literature. I'm not going to mention the detail here, but you can really see a detailed discussion in our paper, which I think is available on the archive now. And there are many references in the past econ literature. But those studies are typically in a slightly different model from us, and also the research questions, the research focus they're having are also different. Many of those works typically look at what kind of how much surplus the principal can derive from the different information structure. But we're trying to understand what joint outcome can happen in this interaction. And this is just for the question 1, and for question 2 about really optimizing information structure. And that's I believe that's mostly open. There aren't that much study. So you could look at a question like, how can I guarantee a fair welfare share between the agent and the principal? For example, how can I design the information structure so that I guarantee principal and agent both get at least 40% of the welfare, right? For example. And maybe you can also maximize some weighted combination of the principal and agent utility, and maybe you want to account for some design constraint. You want to guarantee it will be almost transparent, under some kind of information loss measure. And those problems, algorithmic problems here are almost all open in this case. Finally, I think I have 1 or 2 minutes left, and I'll very quickly talk about information design with commitment. That's the chip talk problem. Most of the information design I mentioned so far, it's all about there's a kind of a commitment, which turns out to be unrealistic in many situations. Example like security or the worship problem or the bargaining situation where the interaction is very limited and there's no way you can commit. And this leads us people to study, information design without commitment, and that's a model called the chip talk, which originates from the seminal work by Crawford and Sobel in 30 years ago. So the model is very similar to information design. I'm actually gonna just skip the definition, but I'll post the. You should be able to see it on the internet about the slides. So it's very similar to information design, except that you cannot commit. And that leads to a different equilibrium called the chip talk equilibrium, which essentially is just a Nash equilibrium, if you want to get an intuitive sense. And the definition of equilibrium is that no player wants to deviate, unilaterally deviate. And it turns out that this can be mathematically formulated as kind of a constraint on the strategy. So no deviation is basically a mathematical constraint, and that leads us to think about some kind of algorithmic question like what's the complexity of computing one chip talk equilibrium or computing the optimal chip talk equilibrium in normal form games like discrete action, discrete state, and under what conditions can the chip talk equilibrium be efficiently computed? Those questions are actually mostly open as well, and we have some ongoing work that are looking at this. We obtained some kind of a preliminary result. Actually, I should mention Konstantin, who is the first speaker for the first part of the tutorial, is really driving force in this line of work. So definitely talk to him if you're interested in learning, what do we know here. And our hope is that we're hoping that we can understand the computational complexity of this problem. Therefore, we can explain, when chip talk is an easy job and when chip talk is a difficult job, it's a hard job. And that's kind of our high-level goal. And really, I want to mention this here is really because I think there's a tons of open problem here in this space. That's all I want to cover, and thank you, everyone.